flat sheet of paper, right? The cross product is supposed to produce a vector that's orthogonal to both of these. But that means the vector it creates wouldn't live in two-dimensional space. It would live in three-dimensional space. And so the cross product is not defined here. There is no definition of a cross product. So what we have to do is we have to extend these vectors into three-dimensional space in order to define the cross product. So what we will do is just convert these into 3D by putting zeros in for the z components. V. So what this will do now is these vectors now that used to be here on the flat sheet of paper are now living, you know, this is like the ground and we have kind of an up and down. We are in three-dimensional space. And now our vector that comes out should either point straight up or straight down. Do you all agree with that? Straight up or straight down. So if the cross product of this, right, should be pointed straight up or straight down, then that means when I set up my little determinants, what's going to happen with the first two components? We should get 0. Let's do it real quick. I, j, k. We want to be able to do these fast. 2, 4, 0, negative 3, 5, 0. Man, that marker's gone. All right, so when I do this, check it out. Crossing these. Cover. What's that? 0. Okay. Cover. 0 again. See? And then here, this piece.
10 minus negative 12.
So 22. That vector is, you know, like if this is the x and the y and the z, our original vectors lived on the flat sheet of paper on the ground, right? And I crossed them, and when I crossed them, I got a vector that is going straight up. Which is, when you look at like physics problems, in two-dimensional space, you have problems, and we'll look at a problem later with torque, where you have like, you know, some, wrench or something that's acting on some bolt, and you're applying a force, right? You have one vector that represents the wrench. You have another vector that represents the force. That's in two-dimensional space. So when you do some sort of cross product, you get this new vector that's orthogonal to both, and that is your torque. And it's either coming out towards you or into the board. And that's your, you have to use right-hand rule. So you're either tightening or loosening, unless it's threaded backwards, right? Because you can have right-hand thread and left-hand thread. So that would ruin your right-hand rule, wouldn't it? All right, so if you want to do torque, I guess what I'm getting at is if you want to do torque on two-dimensional thing, you have to extend your two-dimensional vectors into 3 dimensions to be able to compute the cross product. All right.
Really, if it was octal or like 90 degrees, it could be any number as long as it was in that direction.
What do you mean? That 0?
Yeah, if it was 0, 0, 22, couldn't the last number, could it be any number if it's orthogonal? Or is that
Unless the length matters.
Yeah, unless the length matters.
And it turns out it does. Because when you talk about torque, you're talking about the length.
Yeah. Okay.
So that vector, in applications, it would matter.
Yeah.
The direction, though, is going to be up or down. Yeah. All right, going back. Here we go. So we've got the cross product, major idea. I think you can take a cross product now. Show that if you cross a vector with itself, you get the 0 vector. What happens if you dot a vector with itself? Take a vector, dot it with itself. You get the magnitude squared. We talked about that last class. This, though, says that if you cross a vector with itself, you should get the 0 vector. Well, the way to check that is just, I'm realizing now why all these markers are in here. because they're all dead. I wish people would just get them out of here. I, J, K. All right, let me take a vector u and dot it with itself. So, cross it with itself. So the vector u, I'm going to call it the vector u1, u2, u3. Understand what I'm doing? Just taking the components, making them up. And then I'm going to do it with itself. u1, u2, u3. And let's do our cross. U cross u. It's going to be a vector. All right, so let's cover this one up. That's going to be u2 times u3 minus u2 times u3. 0. All right. Middle one. This is trivial, isn't it?
Yeah.
This is trivial. But this is the 0 vector. Now we start getting into some problems that we definitely will need as we proceed. Find a vector that is perpendicular to a plane that passes through these 3 points. So somebody gives me 3 arbitrary points in space, not vectors, but points. And then says, find a vector which is perpendicular to that plane, essentially. Right? So how could I do that? I'll put the points first. Let me draw them. Go ahead.
You could create 2 vectors that connect to a point and do the cross product of that.
Yeah, so these are sitting in 3-dimensional space, and I will just label them however I want here. Y'all understand that when you're in 3D, you really don't have to care about what order you put these in, because your perspective point can be anywhere, so put them however you want. So we've got these 3 points in space. They kind of already create this plane, and now you're saying to find it, all you have to do is create 2 vectors, right? Just create 2 vectors, and it doesn't matter where they are. Just go from one point to another, and then any other point to any other point would work, wouldn't it?
Yeah.
Except you can't go that one back to that one, right? If you went here back to here, then that would be that vector the other way would be a scalar multiple. Basically, those should dot to be or cross to be 0. So, yes. So let me just do this one. This one makes most sense to me. We'll call that u, and I'll call that v. And so what is u here? U for us. What's the vector u? Notice where my arrow is, all right? My arrow, I'm ending here, right? So I'm going from here to here.
Oh, so it's -2.
-2, take away 1, right? So -3. 1. -7. Okay, so that's last class. How do you find the vector between 2 points? All right, next one, v, 0. -5, -5 again. Okay, now I need to cross them, right? I need to cross them. So you know how I've been doing IJK and then I've been doing all that? From here on out, you're going to see me, when I know I have to do a cross product, I'm going to start writing them out like this. And then underneath, I'm going to be ready for the cross product, and then I'm going to just do my covering right here. I'm not even going to do IJK anymore. Does that make sense?
Yeah.
So now, why is it again that you said to create 2 vectors and cross them, right?
Yeah.
Because this will essentially do what we want, right? It'll give us something coming out of the page,
Yeah.
right? Orthogonal to both vectors means orthogonal to this plane. So what is this here? -5 minus 35, right? So -40.
Yeah.
Cover up 15 minus 0, but then you have to change the sign. So -15. And then this last one, 15, take away nothing. So 15. So your answer here would be right. This answer is correct,
Yeah.
and so is that one. Right? Any multiple of this is correct because the, the vector just has to be perpendicular, right? So the direction is all that matters. In this case, I just take that, I just multiply or just divided everything by -5 to create that.
-3, 3.
Yeah.
Negative.
No, he also negated it. He just put it.
Negative.
Never mind, I'm sorry.
No, it's okay. You could do -8, -3, +3. Any multiple or scalar multiple of this thing would satisfy the result. I only did that because I just want to make sure we all understand that. We're good. Okay, how are we doing here? 30 more minutes, and we'll be halfway. All right, here's a very nice result. Actually, kind of a magical result of the cross product. If you take two vectors and you take their cross product, and then you look at its magnitude, the length of that vector, then that's equal to the length of u times the length of v times sine of theta. Does that not look very familiar? We had something from last class that said when you do u dot v, it's equal to magnitude of u times magnitude of v cosine of the angle between them, right? That was from last class. This is saying that the magnitude of the cross product is equal to magnitude of u, magnitude of v, sine of theta. So very interesting result. I'm not going to prove that one to you. I proved that one to you, didn't I? I showed you this proof in class. I'm not going to prove this one to you, but you could do it in a similar fashion, drawing triangles and taking lengths. Won't do that for time. But what's nice about this is it gives us a way of checking something. What if the angle between your two vectors, right, that you're crossing, what if the angle between them is 0? Then sine of 0 would be 0, right? And then all this wouldn't matter, which means that the magnitude of the cross product would be 0, which means that the cross product vector would have had to have been the 0 vector. So you know how with the dot product, if the dot product is 0, we know that they're orthogonal? This is a way you can check to see if they are, if the angle between them is 0, then they are scalar multiple parallel, right? This is a way to check to see if two vectors are parallel. Is just take a look at the magnitude of the cross product. If it's 0, you know they're parallel vectors. That's a nice formula, but it's definitely not as important as the one for the dot product over there. Yeah, that one's not worth it. So, this is the major result. Two non-zero vectors u and v are parallel if and only if their cross product is the 0 vector. Now here's the one that I think is magical. Sorry, I kind of jumped the gun on this. If you take two vectors, where are my vectors? Come on, where'd y'all go? There y'all are. There you are. I need to make you be able to see this vector, these vectors. There they are. Yeah, that works. Okay. I'm trying to find out where that is. There we go. I think y'all can see that okay. Okay, what I have here is a black vector, u. Actually, I have that backwards. I have this red vector, u, and this black vector, v. And I've had the computer calculate the cross product and give me that vector. So there's that vector that's orthogonal to both, all right? It turns out that the area, you see this parallelogram formed by those two vectors? The area of that parallelogram is exactly the length of this vector. That vector's length is equivalent to the area of that parallelogram. It's amazing, but it's a major result. Can you appreciate the significance of that? Let's see if you can appreciate it. Let's see. There. Here, let me reformulate this question in a different. What if I were to have walked into class today, and we would have said, hey, we have this point right here, and then we have, let's say, the projector, and then I give you some other point like right here. Those 3 points, and I ask you to find the area of that triangle that I just created, right? That'd be a very difficult problem, wouldn't it? I mean, just an arbitrary triangle in three-dimensional space, right? Just somewhere floating around. It's a very challenging problem to find that area. What the previous note says is that if you give me 3 points, doesn't matter where they are, right? 3 points, that if I create a vector going from here to here, and then another vector from here to here, right? Then I can find the area of the parallelogram formed by those vectors. I can find the area of that by just taking this vector and this vector, crossing them and finding the magnitude. So the area of the triangle is just half of that. Right? So this problem right here, as long as I know what this point is, as long as I know the x, y, and z coordinate of that point, the x, y, and z coordinate of that point, the x, y, and z coordinate of this point, doesn't matter how this triangle is oriented in space, I can create the vectors cross, take the magnitude, take half, I'm done. Right? All those computations are arithmetic. You could teach this to, I'm trying to think. I mean, right, like, it would be difficult to walk up to a 9-year-old and be like, okay, you're going to need to do some integration by parts. You might need some partial fraction decomposition. Like, you can't do that, right? But I'm pretty sure you could teach an 8 or 9-year-old how to do a cross product. It's just arithmetic, isn't it? Yes? So this is to me, like a pretty big deal, right? Because we're taking a very difficult three-dimensional problem and just turning it into an arithmetic problem. All right, so let's do this. Let's label these. 1, 4, 6. Wait a minute. Were these the same ones we had a second ago?
Yes.
Are they? Because I thought I made up my own example. No? We did do that. Okay, great. So we had already found, didn't we already find the answer to this? What was the answer to this when... What was it when we said, we were asked to find a vector, right? And I gave the answer like 8, 3, negative 3. I changed it. But what was the original answer?
Negative 40.
Okay, it was negative 40, negative 15, 15?
Yeah.
That was our original cross product. So all we have to do now is take that, take its magnitude, and take half. Don't forget the half part, right? Because it's the triangle, not the whole thing. So I need to take the area of this will be half of the magnitude of that. Which is half of square root of something. I don't feel like doing it. You get the idea though, right? I mean, it's just an arithmetic problem. Square that, square that, square that, add them together, take the square root, take half, you're done. So pretty nice, right? Yes, thank you, thank you. I mean, there's some results that are pretty profound. I mean, I think this is a profound result when you just think historically how difficult it must have been to not have this and have to find the area of some triangle that's not laying on a flat sheet of paper. If it's on a flat sheet of paper, then you're fine because you've got, Pythagorean, you've got law of sines, you've got law of cosines, you've got all these different formulas for areas of triangles. But as soon as that thing gets tilted and it's no longer on a flat sheet of paper, it's in three-dimensional space, things get messy. All right, we're moving on. What if you have three vectors? So now, you know, this one's hard to show, but let's say we have one vector here. We have another vector here. So I can find the area of the parallelogram of these two, right? But now I add a third vector. Put them all tail to tail to tail. Then I get like these two create a parallelogram, right? These two create a parallelogram, and these two create a parallelogram. So all three of those vectors create this three-dimensional, there's got to be a name for it. Yeah, it's up there. Yeah, not doing too good. Is that okay right there? That is a parallelepiped. That's the name. Okay? These don't have, that looks like almost like a shoebox. It doesn't have to be shoeboxy. Everything can be kind of twisted. Let's see. Yeah, there we go. Skew it out there. So that right there is called a parallelepiped, but it's created from three vectors instead of two. And we can find the volume of it using what's called the triple product. So look at what it is. You give me three vectors, and you want to know the volume of the parallelepiped formed by those three vectors. All you need to do is take the cross product, right, of any two vectors. After you're done crossing those, you'll get a vector, won't you? Dot that vector with that third vector, and then take that answer and take its magnitude. Now, can you tell me right now, is that right there a vector or a number? That's a number. Because those two are a vector, right? That's a vector. Dotting a vector with a vector is a number. So why the absolute value then? It could be negative, right? Because dot products can be negative. Remember, if the angle between two vectors is bigger than 90 degrees, it could be negative. So we do the absolute value because we don't want our volume to be negative. That one I haven't seen used as much, but that is a result. I don't think I'm going to go through this example because I think you could do it. Am I too, is that all right? Or, right, find the volume. So pick any two, cross them, right? After you're done with that, dot it with the other one. Take the magnitude, you're done. Take the absolute value, sorry, you're done. Okay, application. Cross product torque, okay, so if we tighten a bolt by applying a force to a wrench, we produce a turning effect. Torque is a vector which represents the tendency of the bolt to turn. Torque is defined to be, torque is equal to R, the vector R, crossed with F, where R is the position vector of the rigid body, the wrench, and F is the force acting on the wrench. The direction of the torque is determined by the right-hand rule. Further, the magnitude of the torque is the magnitude of the cross product, which is that formula that we had a second ago. This is actually pretty important. I'm going to show you something now. So here's my wrench. Okay, so I have a wrench. I'm going to turn a bolt right there at the origin. I have a wrench here, and then I have a force. So I'm going to just pull my wrench straight out to the side, and I'm going to apply a force perpendicular to that wrench. So I've got my, I go in, I'm trying to get a job, and they put me on the job for a week to see what I'm doing, see if they like my work. So I go out there and I get my wrench out, I'm going to tighten a bolt, and I apply a force perpendicular to the wrench down, and the supervisor's like, let's keep them. So why is that important to be perpendicular to the wrench?
It's the most force.
That's where you're going to get the most torque, right? Because why?
Since it's a sine function.
That's right, because the magnitude of R cross F, that's the magnitude of your torque, right? And this, by definition, is the magnitude of R times the magnitude of the force times sine of the angle between the two vectors. So if your wrench, as long as your wrench doesn't change length, okay, in the middle of the turn, and as long as you apply a constant force, then these two are not changing, right? The only thing impacting the magnitude of the torque is the angle between the two. And so to make this the biggest it could possibly be, we want this to be 1, don't we? Because sine is bounded between -1 and 1. So if we make that 1, then we have the most torque possible. And sine of 90 degrees, or sine of pi over 2, is 1. So that's what we want, right? Now what would happen if you came in here and you made the angle between these two vectors 0? Right? So this is this other guy. Well, maybe this would have been me. So here I am, and I'm applying my force directly into the wrench and getting 0 torque, right? Just pushing the wrench against the head of the bolt, right? I mean, it's obvious that this is ridiculous to do that, but we're getting 0 torque because our angle is 0, and therefore the magnitude of the torque must be 0, right? Now what happens if I go the other way? So when I did straight down like this, awesome, I was getting a certain torque. Which way is the torque vector? Where's the torque vector going right now? Is it coming out towards us, or is it going into the page? So put these two vectors together. Be careful, R goes from the origin out, so here's R, right? The F vector goes from the tip down here, and now I'm going to put them tail to tail. So my F vector is like this. The torque is R crossing F. R crossing F. So here's R, here's F. Right-hand rule, my fingers need to be pointed out R and curl towards F, which is this way, right? Like this. R crossing F. And therefore, the torque vector is going to go into the page, which makes sense. When you go like that, the bolt wants to go in, so long as it's threaded right-hand rule, right? Or right-handed threads. That's what they call it. Right-handed threads, right-hand rule. It's all tied together, right? Okay. Now, if you take your force and flip it over, and you're now going to loosen the bolt, all that's happened now is this vector is now up here, like that. Right-hand rule, R crossing over to F, coming out at us. What about, we're getting close to a break here. What about this? What if we had this weird thing? We had all right, so what I have here is this. I have a pivot point here. So imagine like a bolt, and I have this weird wrench that goes out 2 feet, down 3 feet. I know it's not drawn to scale. And I'm going to grab this point. So this is like an L bracket or something, right? And I'm going to grab this point, and I'm going to pull like this with 30 pounds of force. And this has an angle of, let's say, to make things easy, 45 degrees from horizontal. Could we figure out the torque vector and the magnitude of the torque on this point? Yeah? No? What would you need? Or would be the only thing you need at this point? Does the shape of this really even matter? I mean, it matters in the sense that you need to know the distance from here to here. But otherwise, the shape could be, pretty much anything. So what you need to do is figure out what this R vector is, right? Now be careful, because you're not figuring out the length of R. You're actually going to figure out what the R vector is. So you need to know some angles and be able to recover the components of that vector. And then once you know that, then you convert this into a vector, and then you can compute your torque. I'm not going to get into this. The homework does get into some of this, so you can practice when you're doing your homework. All right, I think that's it for that section. Yeah. Okay, let's take a break. It's 3:30. We will come back. Let's go 15 minutes. 3:45? Do y'all mind, or do y'all... I forgot to ask you, do y'all want these breaks, or would you prefer to not have a break and end earlier? Y'all think about it. We can talk about it later.
That's a dilemma.
my microphone. Standard equation of a line, two-dimensional space, right? And we are not going to do this. I mean, this we all know, right? We've seen this, we've dealt with this. We know the slope of a line, right? Slope, this is the y-intercept. We've seen it. What we're going to do now is we are going to talk about how you draw lines in three-dimensional space and two-dimensional space. We'll kind of kill two birds with one stone. So let me reevaluate this notebook real quick so everything goes back to the way it started. All right, so before I can do anything, I need to make sure you understand this, that if we are given two vectors, R0, and let's say R1, and we put them tail to tail, then if we compute R1 minus R0, this will give us a vector that goes from the tip of R0 to the tip of R1. So the vector that goes from here to here, this vector, is R1 minus R0. Do you all agree or disagree? Agree? Remember, this is R1 plus negative R0. That's what this really means, right? And so if I take R1, which goes from here to here, right, and then I add to it negative R0, negative R0 is that one. So if I take that and slide it here, right, this is negative R0, oops, negative R0, then the result, this result means I'd start here, I'd go up, and then I go down, so I'd end up here, so I get this vector going from here to here, right? Now if I take that vector and I slide it up, it's the same vector, right? So this subtraction of these two vectors, R1 minus R0, results in a vector that goes from the tip of R0 to the tip of R1, all right? We need that preliminary thing to get started here. So now we talk about the vector equation of a line in two-dimensional space. So we know what a line looks like in two-dimensional space. We can also visualize this line as just a bunch of points, right? And each point that we have on that line corresponds to some vector. So there is a vector that points to every point on that line, right? So another way we could draw a line is just give you a formula that draws all those vectors, right? And that would give you a way of drawing all those points. So our goal here is to try and come up with a formula that generates every single one of those vectors that you see there. So that's what we're going to go about trying to do now. So infinitely many vectors is what we're going after. So here's how we're going to do it. We're going to start first by having what we call like an initial vector, which is a vector that goes from the origin to a single point on that line, right? So that we're going to call R0. And then after we have that, we're going to have a second vector, R1, which goes to some other point on that line. Now, remember, what is it that you need to define a line? Like, if you want to define a line, you have to have what? Slope, right? Y equals, so, or in a y-intercept? Or you can have a point and a slope, or 2 points, right? So there's a bunch of different things that you could do to get a line, but the minimum information you need is either 2 points, a point and a slope, right? Or a slope and a y-intercept, which is the same as a point and a slope. So what I'm saying here is, let's say we start with 2 points on a line. We're going to create two vectors, the vector that goes from the origin to that point and the origin to that point, right? So we have this R0 and this R1. Now what we're going to do is we're going to create a vector V which is the vector that goes from the tip of R0 to the tip of R1, which I think I just explained to you right before we started, that the vector that would go from the tip of this to the tip of this is just R1 minus R0, right? Okay, so that vector V lives on that line, doesn't it? That vector V points in the same direction as that line does. All right, so we started with 2 points. We created a vector and a vector. We did this vector minus this vector to create that vector. Now, imagine, if you can, that to get to another point, not these 2 points, but to get to another point on that line, what I would need to do is just go R0 and then follow V, and maybe like V times 2 would take me here, right? R0 and then V times 1 would take me here. And if I do any multiple, sorry, I have a better animation here. Where is it? Here. If I go R0 and then 1V, I'm here, I can do any multiple of V, and that would stretch me out to another place on that line. I go negative, then I'll go the other direction, right? So I guess what you need to see is that our goal is to start with an initial point and then be able to generate all the scalar multiples of V that would move us back and forth along this line. And so here's our general formula that we're going to use. And I'm going to write it down over here because we're going to need it. R of t equals R0 plus TV. So we'll discuss this, what this formula represents. This is the initial vector, R0, that got you up to the line, right? This right here takes you from the origin. There's our line. It takes you to the origin to some point on the line. There you go. There's R0, that vector. And then what we're going to do is we're going to add to it multiples of V. And V is this vector right here. And we're just going to scale that V times some arbitrary number, which is going to stretch the V out this way and go that way. So the R0 right here, this vector, comes from some initial point. Someone has to give us a point on the line. And then V is this thing that we call a direction vector. So let me scroll down because I think it says it under here. Oh yeah, direction, sorry. V is the direction or direction vector of the line. Now, I want to get to an example. I'll come back to these notes. I think it's best to just get to an example. Okay, so we're going to do a two-dimensional example first. I'll leave that. All right, so what I want to do is take the point, these are points, 3, 6, and 7, 14. And we want to find the vector equation of that line. So that's an equation that generates all the vectors that draw the points on that line. So I know it needs to look like that. This is the vector equation of a line. And so let's start filling in some pieces here. What about the R0? Where does R0 come from? So try and visualize this. You have a couple of points here, 3, 6 here, and then 7, 14 here. You got 2 points on this line, right? Okay, so R0 is going to be what? We can do either one of those points, right? We can use either one of these points, and that will convert that point into a vector, and that will be our R0. So our R0 will be the vector 3, 6, and that gets us started. That takes us up to the line. Now what I need is my V. My V is my direction vector, which is the vector going from this point to this point, isn't it? It's the vector that connects those two. We need this V. So how can I get the vector connecting those 2 points? Just the same way we've been doing it, right? You just take that one, you're going from here to here, right? So what is the vector going from here to here? So 7 minus 3 is 4, and then 14 minus 6 is 8, right? So this is our direction vector. So if I go out 3, 6, and then go and add the vector 4, 8, I'll be here, right? But if I take any multiple of that v, that'll take me to my initial point, and then it'll stretch me, maybe halfway or twice as much or backwards. So it should be 3, 6. The vector equation should be 3, 6 plus t, right, times v, and v is 4, 8. Does that make sense? So this right here is the vector equation of that line that connects those 2 points. This is it right here. Let's just check to see real quick that this does do what it's supposed to do. What happens if I plug 0 into this vector function?